This is finishing off the stuff from Friday. Yeah, this is on the Friday note sheets. Yeah, some of you are looking going, I didn't pick that up this morning. This is the second half of the note packet that we started back on Friday. They're like, oh, that's what he's been talking about this whole time. So, quick explanation while some of you are looking for this. Intercept form, okay, is another one of those things. The order of finding things is going to be a little bit different than it was before, but I'm still going to end up finding all the same values that I was looking for in what we were doing Friday. Except now this time, I don't find my vertex right away. It's actually one of the last things that I'm going to find. What I'm going to do this time is, since it's in intercept form, I'm going to take each of these quantities, each of these sets of parentheses, and I'm going to set them equal to 0 to find what the actual x-intercept on my graph is. Now basically, I don't need to write this out as an equation. I mean, I don't need to sit and write x plus 3 equals 0 and x minus 5 equals 0 and go through and solve it. You can basically look at it and say, oh, so basically, Harty, you're just switching the signs on me. Yes. Okay? So my x-intercepts are at -3, 0, and 5, 0. And I can literally plot those points right away because that's going to come in handy for my next step. Once I have my intercept, the vertex is going to end up being right in the middle. So to find your x value, you can do one of two things. You can either go old school here and say, if I want to find the midpoint, I'll just kind of keep coming in from the edges until I get to the middle. So I look at that and go, ooh, my x value here is 1. Now, I'm not putting a point there yet, but I know that's going to be my x value of my vertex, that midpoint. And once I get here, just like I did before, well, I'm going to plug that 1 in. So to get the y value, I'm going to do 1 plus 3, 1 minus 5, and I'm going to multiply that together. I'm going to take the product. 1 plus 3 is 4. 1 minus 5 is -4. So 4 times -4, -16. So my vertex is at 1, -16. The thing that you'll like about this is we're not going to deal with 5 points. We're only going to deal with 3. Once I have my 2 intercepts and my vertex, we'll just go ahead and make our parabola through that. So in some ways, like, ooh, this is kind of shorter. This ain't bad. I'm still going to draw in my axis of symmetry. Never want to forget about that. And basically, with intercept form, that's it. So it's nothing that's too bad. Now, with the intercepts, if you remember back to geometry, you also can do it like the midpoint formula, which is what I'm going to actually do on this second one. So I get here. I notice a couple of things. What way is my parabola going to open in number 8? Okay, how do you know down? You're right. Okay, it's a negative out front, so my parabola, my U, is going to open down. So I know that. Where are my x-intercepts going to be? Yeah, they're the opposite of what you think. So 1 and -3. 1 and -3. Now again, I could just kind of use my fingers and count into the middle. But if you're more about, well, what happens if it's a fraction sometime or something like that? What I'm going to have to do in that case, what I would do is I would take my 2 intercepts, 1, -3, and just add them together and divide by 2. That's going to be my x value of my vertex. So 1 plus -3 is -2. Divided by 2 is -1. But I'd have gotten the same thing if I'd have just used, 2 pens or my fingers and just worked my way to the middle. So I know the x value of my vertex is -1. So now to get the other part, I go, okay, So -1 minus 1, -2. -1 plus 3 is +2. But remember, that negative is still lurking. So -2 times 2 is -4. Then change the sign. +4. So my vertex is at -1, +4, and that makes me feel pretty good because I know it's going to open down. So as soon as I see that, go ahead and make my parabola. And where's my axis of symmetry going to be? X equals what? -1. Okay, whatever the x value of my vertex is, where my axis of symmetry is going to be. Flip my graph, and I'm good to go. And that's not going to change at all through these, because even when I get over to number 9, okay, when I go to find the intercepts, I still ignore the values outside. This just tells me how much it's going to stretch or shrink. So when I go to do this, okay, where are my x-intercepts going to be for number 9? 3 and -1. 1. So with that being the case, where is my x value for my vertex going to be? Please, not another 1. 1. Okay. So once I know where that middle point is, my midpoint of those two are, take that 1, I'm going to plug this in. I got the 2 there already. 1 minus 3 is -2. 1 plus 1 is +2. And you're like, you know, Harty, I've noticed something. It was 4 and -4 the first time. It was -2 and 2 the second time. Is that going to happen every time? Yes. If you found the right vertex, these two values will end up just being opposites or inverses of each other. So 2 times -2 is -4. Times 2 is -8. 1 -8. I feel good about that because it's a positive coefficient, so I know it's going to open up. Go ahead. Connect it up. Where's my axis of symmetry going to be? 1. X equals 1. Whatever that x value is going to be in my vertex. Now we have to get an application problem in. I mean, my gosh. Got to get you all ready and thinking about stuff you want to get towards the ACT coming up. Well, for some of you, yes, it's going to be a little longer than others. But it still will come sooner or later. So here, all right, we have the Woodland jumping mouse, and how some of you freaked out about box elder bugs. I'd love to see what you get around a mouse. So, can hop surprisingly long distances given its small size. This hop can be modeled by this following expression. Now, this is in fact kind of an intercept form again. Except now, instead of having two quantities, two sets of parentheses, this first one's just kind of on its own. So when I go looking for my intercepts, I'm going to take each of these values, and I'm going to set them equal to 0. Whoops. So what are my two x-intercepts going to end up being for this particular parabola? 0 and 6. Because if I do all this work, I'm still going to get 0. If I add 6 here, I'm going to get 6. So I put a point at 0. I put a point at 6. You're like, well, how did that just tell me how far it can hop? How far is it from 0 to 6? 6. So it's actually the distance of the x-intercepts, the width of my parabola that would tell me how far in this particular instance this would be. So to figure out how high, I notice this is going to be opening downward. So wherever this vertex is, it's going to tell me that. So let's see here. Where's my x value for my vertex going to end up being? 3. Okay, so my vertex, I've got 3, and then I've got to plug that in to get my actual value to see how high this is going to be. So I've got negative 2/9 times 3, and we got to do 3 minus 6. So we got a couple of things going here. Bless you. Negative 2 times 3, because I'm just going to work on the fractional part first. Negative 6 over 9. Negative 6/9 is negative 2/3 if I reduce it. I've got negative 2/3, and 3 minus 6 is 3. That turned out kind of nice. Negative 2 times negative 3 is negative 6 divided by 3 is 2. My vertex, oops, oh, Harty. Why do you not use pen when you're doing these things? And the Woodland mouse looks as though it could jump 2 feet high. Okay? But that's where an actual application come in. And no, it's not just with mice and jumping and things like that. That can be things you could use with, figuring out the trajectory of a missile. Okay, for instance, if you were doing war-type applications, back in the day, if you were using catapults and things, you could do that too. And that's kind of how this would work. Yes, back to the barbaric ages, yes. So, now we've made it to a point that we can handle the end of these, but then we're also going to be working, and I will get a couple of those up just to kind of remind some of you how they work, and that breaking down square root sheet that you picked up from the front, which I'm actually going to stick a couple of up right now, just to reminder of how this works. Let's jump back in here. Yes, that actually would be better. I can get you hooked up with another piece of graph paper if you need it. Yes. Okay. So that other sheet that you picked up, remember back to when we were talking about all of these perfect squares. And basically we were just talking about these, but we may run into one or two that are a little bit larger than this. But basically when you're reducing a square root, what it comes down to is you're finding two numbers that multiply to the number underneath, no matter how ridiculously large it may seem. And you want to make sure that you get the biggest one. Otherwise, you're going to have additional work to be dealing with. So for instance, one of my two numbers has got to come from the list. No choice. What's the biggest square root that you see up here that will go into 48? 16. So 16 times 3 is 48. They're both still square roots. But the 16 is perfect and gets out of radical jail. 4, new identity. 3 is not in my list. It is still acting irrationally. So it has to stay underneath. This is all about doing mental math. Sure. Okay. I think I was just told I was mental. Okay. So now sometimes this may be easier than others. You may start getting into some numbers here like 10 and 12. You're like, oh my gosh, how the heck is this going to work? I mean, I don't even know two numbers. I'll multiply to 294 period, much less make it all. Which is where at that point, personally, I would start taking those numbers in the list and I'd try to divide some in until I found one that went in nicely. But yes, if you get to a point, I don't remember which one we were just doing, 10? 49, so I'll call it 49 and 6. Okay, there will be something that works here. Square root of 49 is 7, out of radical jail. 6, yeah, not quite so much. And then just one more reminder with this. Well, if you put your perfect square first, yeah. Yeah, whatever your perfect square is, whatever number is coming from this list is the one that's going to be on the outside once you break it down. Okay? Well, what if there's a number outside already? Like, what if I'm doing 21? I'm going to ignore the 2 for right now. 2 numbers that multiply to 96, one of them's got to be in your list. Yeah, we'll just wait for someone to tell us. Oh, well, this one we got to keep working on knowing the list. About 16 to 6. Okay. This is the nonchalant, Harty way of saying you've got to get at least these into your noggin. Because otherwise, this is going to get to be a pain as I keep firing these your way. All right. So square root of 16 is 4. Square root of 6 is itself, but that 2 is lurking out there. 2 is very happy that this got out of radical j, because now they can hang out. 2 times 4 is 8. Square root of 6. Okay. Some of these will turn out really nice. You might even get a perfect square or 2 in there, or you don't have to do much of anything. Okay. Another one's just going to be a little more work. So this, and those last 3 problems from yesterday, and I will get some more graph paper here, are what you've got, excuse me, on the